So in the morning we saw that the sum, like summation over mu t md, this is actually like the product 1 product over p 1 minus fp, right? But p is varying over the divergence of t. No, p is varying over the divergence of n. So this summation md mu t or mu t md. Mu t is the sum where d is dividing in this is 1 minus f t into the minus n, whenever f is a multiplicative function. For all multiplicative functions, and then we commented that we can now get the expression for phi n in this manner. Okay. So how do we define phi n? The number of positive integers which are less than or equal to n and O prime n. Right? So you have phi n as the sum of I, G, C, D in K, where K are here, K is varying over A1 to N. Right? So if this is 1, you are having 1, otherwise you are having 0. Now recall, I was the convolution of mu and u, right? The Mobius function and the unit function. So this was mu star u dCt of A and K, right? And that is, now if you write the convolution out, what does it become? A run from 1 to n summation over d dividing the dCt of n and k. I am now only the dCt here, but it's understandable, yes. Mu b and u d by d, right? But u of n by d is just 1, right? So this is, so you can remove that u by d. So this is this part. Okay. Now, note that all these are finite sums, right? So there is no problem in switching.
But k is running from 1 to n, so you have to switch.
Right, we have to write this out a little more clearly, so I'm going to say k is running from 1 to n, and this is d dividing n and d dividing k. So what we will do, just a minute, we complete this. Right? So what we will do, we will fix a d which is dividing m. Okay? And then, so, wait a minute. Here we do some. Wait, we took the. Yeah, right.
So isn't it m comma k by d?
M comma k by d. No, we are taking. Right. There it should be a comma k by d. Should this. This is the of now what we are going to do here, we're altering the sums and we're fixing a d which is dividing m, and we'll count the number of k's for which that are well, what are we summing for such a d? For such a d, we are summing mu d over all the things which are
common divisors of the
yeah, right. But if you fix
N
n
fix a device k will be a multiple of d.
exactly, you're looking for the multiples of d. Okay. So things in dz intersection the integral what way. So that is summation d down n summation over well now this k is in dz intersection 1 to n. Okay. And what are you summing? You are summing over this mu d. That is, and you see, for this you are just summing mu d. It's not depending on k what you are summing, so you can take mu d out. Summation d dividing n mu d, and now what you are doing, you are counting the number of k's. So you are summing over 1, sorry, summing 1 over this set k in dz intersection 1 to n. Okay. How many k's are there in this interval? That is, how many multiples of d are in this interval 1 to n?
N over d.
Is that n over d? D is
Divisors.
divisor of n. So since d is a divisor of n by d is an integer, so you can just write it out. So this is mu d times n by d, or n times summation d dividing n mu d times 1 by d, which is exactly, that is inside the sum we have such a thing, right? So we can just leave this in there, and this is the product by n in the outside, and this sum now we can replace by 1 minus this one, because 1 minus that is this function is a completely multiplicative function. So this is the product over p divided n 1 minus 1 by d. Alright, so now we are going to talk about Dirichlet series and its relation with convolution. So here's a small theorem. Let the summation if n running from 1 to infinity is 1 by this. So before starting the Dirichlet series, suppose we have such a series which is convoluted. Converting absolutely. Where if is a multiple. Then we have this summation being run from 1 to infinity. If n this is equal to the product over the product over primes in if you number the primes from like p1, p2 or well, pk, then you can write this as product over k running from 1 to infinity sum over if pk 1 to n k. Just a second. N is running from 0 to so proof. At first, what we do, we take some n, which is this product. Pk we call mk, and a is running from k is running from say 1 to some r. Okay. And of course, here we are adding this n case also to be 0 because we are taking the first r prime numbers and we are writing n as pk power nk. So sum of these n k's is 0 and some are not. So this is that is giving you the prime product decomposition of n. Okay. Now we will write what is f of n in terms of this. We will know how to write this. Right? So we know that f of n is product over n running from 1 to r if pk we got nk. Right? So suppose now you want to write the sum over b dividing n. So if you have here, then it's a sum over. Well, you can also write it in this manner. Product over k running from 1 to r if of pk. Well, now you take the sum inside because there's a multiplicative function. You can of course do this. That is write it as a sum over f pk n, where n is varying from 0 to nk. Right? N was this product pk. So any of its divisors d should be of the form k running from 1 to r pk or something
which is less than equal to n.
So then all of these are captured in this product. Now note that if you let this r go to infinity, so here, wait a minute, instead of n, we will write this, we divide k running from 1 r pk will go nk. Now note that if you let this r go to infinity first, and then also let this n case go to infinity, what you are having on the left, the product, sorry, sum over all the integers, because you are having all the integers to do it in this form. What you are having on the right. So here, at first you are having an infinite product, you are letting r go to infinity, and then inside you are having infinite sums. And the left hand side, well, and we get the convergence of both sides by absolute convergence. Because I mean, we are given that the series convergence absolutely. So So you are allowed to rearrange the sums and sum in whichever manner you would like to sum. So R so we obtained this by the fundamental theorem of arithmetic, right?
Sir,
Yes.
just to clarify.
Yes.
So that was f of n. When I did not get it.
Yeah, sure. Yes.
The step here, that summation f of d,
Summation f of d, right?
and d are the divisors of n.
D is the divisors of n, and then
Why did it become the same as this on the left?
the left hand side by the fundamental theorem of arithmetic, because it says that every n has a prime decomposition in this form. And now you are taking the number of primes arbitrary large, and you are taking the powers arbitrary large as well. So you are capturing all the integers by the fundamental theorem of arithmetic, because every integer has a reciprocal decomposition. Right? So this sum runs over all the integers, and on the right hand side you are getting both this product and this sum which is infinite. Gives one infinity f of n is the sum, sorry, the product a running from 1 to infinity and the sum n running from 0 to infinity if pk. So now we define, is this already in front of you? So definition of formal indices. Okay. What does it say? Well, so how do we define a formal indices? Suppose you have a function. Suppose you have an analytic function with a to c, then the formal decrease is associated with f. We denote by dfs as sum over fn by n power s, where n is radical. Formal means that at present we not care about its convergence of dimensions. We can just define this way. Now, well, at first note one thing, that if f is multiplicative, then for DFS, what we will suppose f is multiplicative and suppose the formal DFS is absolutely convergent. coordinated series associated with f is absolutely convergent. Then what we have, we can write it as this is called Euler decomposition. If is a multiplicative function, such that dfs converges absolutely, then dfs is equal to this product a running from 1 to infinity sum over f just not fpk. But below we will also have this pk power ms, and everything is running from 0. Wait a minute. So this
m from 0 to infinity.
So this is called the Euler decomposition of the Dirichlet series associated with if.
Multiple.
Yeah, if it needs to be migrating for upwards. You can do something. So, yeah. If is complete multiplicity, then we can write this as fpk for n, that is fpk by pk whole power pks whole power n.
Whole board. Geometry.
Right. Then this becomes dfs product a running from 1 to infinity summation m running from 0 to infinity if pk by pk's n, right?
In order for convergence, you need f pk divided by pk ps, that must have absolute convergence.
Right. But nevertheless, you know that this is
This
also
converges.
right. So this is nothing but 1 by 1 minus pk by pk. So here's the next theorem which relates convolution and Dirichlet products, and this is this. So if let f and g be arithmetic functions, well, suppose f and g are arithmetic functions, and then we are going to write then if star G is converges absolutely, so let f and g be arithmetic functions there, and also assume that these converges functions and let G is converge then we have H star G equal to if d star GS equal to DFS and DGS, and in particular both of these also converge absolutely. And vice versa. And if we clear from then we can also go with the reverse direction. So let's write this down. P equal to GS is by definition if star G of n by n power s, where n is running from 1 to infinity. This is summation n running from 1 to infinity, summation d1 d prime, we can just write d prime is equal to. So n you will be composing as product of d and d prime, and you are writing this f d g d prime d power s times d prime power s. Okay. So this one now. This is just a, well, you all, once you write this, you know that this one converts absolutely, right? And so this sum, now you can sum it in a different way. Let's switch the sum.
Star D equals 1 to infinity,
Right.
and then n would be a multiple of D.
Right. Okay. So d running from 1 to infinity. And that means, now if you want to fix n to be multiple of d, all you care is that you take some d prime and let it vary from 1 to infinity as well, and multiply it. And then now separate the things. So you have d running from 1 to infinity is d by d power s times summation d prime running from 1 to infinity dt prime by d prime power s. So here you have dfs and here you have dgs. So that is equal to, this is equal to dfs times dt. So we prove that these two are equal. And we just used the absolute convergence to shuffle this, to switch this sum. On the other hand, if we know that now that both of these converge absolutely, then you write them here, and then you do this one, and then you go back to this.
Here, power is exponential.
Right now, what we have from here, we define zeta is by this sum, right? In value from 1 to infinity, 1 by importance. Okay. So can you recognize which Dirichlet series this is?
For f is 1.
Yes. So D U is.
Oh, right.
And well, at first we have this is a multiplicative function, right? So we have the Euler decomposition. U is just consider U as a function. So since you know that for an arithmetic function, you have the Euler decomposition of the Dirichlet series, you can write this as x in a commutative multiplicative function. So you can write this as summation in the value of 1 to infinity 1 by 1 minus 1 by what's product. Ah, right, yeah, correct. Yeah. Thank you. Yeah, we are calling it. So you know Euler decomposition. Thank you. So we can write this as a product. 1 by 1 minus 1 by power s and p prime. So for all the primes, so it is correct. This is called the Euler decomposition of zeta. And zeta you know is dus. So what is d mu s? By the way, recall this that mu star u is direct function. And we know that if you have absolute convergence, then these two are the same.
So d of mu.
So why do you have the absolute convergence?
Oh, for real part of x greater than 1.
Right. So this converges absolutely. Not that. Beta converges absolutely. Absolutely for yes. Right. So in that region you have the u star mu as the u s times the s. And dux is just a zeta function, right? And what is du du star mu, that is di is, right? What is di is?
1.
It's 1. Because only I1 is 1, that is to 0. Right? So you can just write this is equal to 1. That means that 1 is equal to zeta times summation. Wait, or you can write that. So from this last equation, you write as summation mu n by n power s n running to 1 to infinity. This is equal to 1 by zeta s all s with real part of s greater than 1. Now what we can do, what else we define this function, right? Rk n was defined as this is k, right? And then we saw that Rk star u is what is what? Rk star u?
Oh, sigma
Sigma k.
k.
So now consider this one. Consider d sigma k is, that is summation over sigma k n by n power s n running from 1 to infinity. Okay. Consider this is. Then what do you get? Yeah.
Product.
Right.
In the region.
So in the region of very converters, you have this thing d of sigma k is equal to d of rk is times, well, dus is just zeta s, right? So zeta s. Now can you simplify this? drk is. So what is that?
1 over a to s minus k.
1 over a to the power s minus k. Okay. And here n is running from 1 to
And
now where does this convert?
real part of s greater than k.
Real part of s
Yes,
greater than
greater
k
than
plus 1.
K plus 1.
And if you let k to be arbitrary, I mean if you also allow k to be fractional powers, then you can take the maximum of, take the max. Well, also if you allow k to have some negative and with negative powers as well, then you need both of these to convert, right? Both zeta s and s. So we take the maximum of 1 and k plus 1.
That is the region of minus first.
Right. So this will give you then. And what this is just zeta. This means right. So what do you have then on this one? D sigma k is just zeta s minus k for all s with real part of s larger than maximum of 1 and k plus 1.